Today I'm just gonna walk you through my proof of linearity of expectations. First, we start with the claim let x1 and x2 be indicator random variables. Then the expected value of x1 plus x2 is equal to the expected value of x1 plus the expected value of x2. First, we start defining a random variable x so that x is equal to x1 plus x2. And then we explain why these can only take the values 0, 1, and 2. The x can only take the values 0, 1, and 2 because we're using x is defined by the sum of two indicator random variables, those being x1 and x2. And the indicator random variables can be either 0 or 1. Hence, we end up with something like this. If x1 is equal to 0 and x2 is equal to 0, their sum is going to be 0. Therefore, x is going to be 0. And so on. If x is equal to 1 and x1 is equal to 1 and x2 is equal to 0, x would be equal to 1 because the sum 1 plus 0 it's 1. Therefore, x is equal to 1. And here you can see the next thing. After that, we define for convenience p and q, where p is the probability that x1 equals to 1 and q is equal to the probability that x2 is equal to 1. And we explain why the right side of this equation, these expected values, would be equal to p plus q. This is pretty evident because we know that the definition of expected value is the sum of the outcome standard times their probabilities. Hence, if we just calculate the expected value for each of these indicator random variables with these definition over here, we end up with just the probability that x equals to 1 for x1 and for the expected value of 1, and the probability that x2 is equal to 1 for the expected value of x2. Since both of them range from 0 to 1, there should be a 0 times the probability that x2 equals 1, as the same applies for x1. But I didn't put that because 0, everything multiplied by 0 is 0, so that amount it's not significant. So since we already calculated the expected values of these two indicator random variables, and we set p plus q equal to the probability that x1 equals to 1 and the probability that x2 equals to 1, we can just notice that since we already know these expected values, we know that this right side of the equation over here is equal to p plus q. I think it's pretty. This is explaining it pretty well. Well, now we reach to the third part, and this third part is where I got it wrong. And the reason why I got these proof wrong was because I didn't have a really solid understanding of probability in general, and I didn't relate my explanation with these part 1 of the proof. So since I didn't relate it and I didn't have a good understanding of probability, I couldn't see that, and I resorted to an example that's totally wrong, that uses specific numbers without a setup, and that cannot be done. So this is the corrected part. And this is the most important part as well. So we know that x is equals, since we have established that x is equal to x1 plus x2, then we know that the expected value of x would be equal to the left side of this equation, right? And hence, by definition, we can express this by this definition we already set here, by the definition of expected value. We can just set this expression over here. We need to again let me just say what we're doing in this step, in step 3. In step 3, we're just showing that this left side over here simplifies to p plus q. So this should be a little bit longer, but kind of straightforward in a sense. So okay, right now we have established that the expected value of x is equal to the expected value of x1 plus x2, which is equal to the sum of these, like to this sum over here. We can notice that this sum over here, we can notice that we can express this sum over here as this over here. Again, there's gonna be a 0, but that 0 gets eliminated because it's not important. Everything multiplied by 0 is 0. So here we just like expanded. Like in this part over here, we just expanded the sum over here. Here. Over here. And we notice that, yeah, like 1 is times the probability that x1 plus x2 equals 1, and 2 times the probability that x1 plus x2 equals 2. Also, since we have established that x can only take the value 0, 1, and 2, and that x1 and x2 can either take value 0 or 1, then we can say the following. We can say that the probability that x1 plus x2 equals to 1 is equal to the probability that x1 is 1 and x2 is 0, plus the probability that x1 is 0 and x2 is 1. Yeah, like if you, and this makes sense, right? Since we have established it right here, right? We just sum the probabilities to get this probability over here. You can interpret this as we need the probability that x1 plus x2 is equal to 1 is equal to the probability that x1 and x2 that x1 is 1 and x2 is 0, or the probability that x1 is 0 and x2 is 1. Again, if x1 is 1 and x0 is 0, the sum of x1 and x2 gives you 1, and the same applies for here. So this is valid over here. And we can also say that for the second term over here, we can say that x1 plus x2, the probability for x1 plus x2 equal to 2 is equal to the probability that both x1 and x2 equals 1. Again, we have established it here. So this is valid as well. We need x1 to equal 1 and x2 to equal 1 so that their sum gives you 2. Now, like, notice that we can substitute these in this expression over here so that we can express this following expression, right? And we can do something really interesting with this. But first we need to establish what do we mean by the probability of x1 equal to 1, right? So since we know that these values range from 0 to 1, we can establish that the probability that x1 equals 1 is equal to the probability that x1 is equal to 1 and x2 is equal to 2, plus the probability that x1 is equal to 1 and x2 is equal to 0. In both of these cases, x1 is equal to 1, so that'll give us the probability of x1 being equal to 1. And the same applies for here. In both of these cases, x2 is 1, so that will give us, in both of these cases, x2 is equal to 1, and that will give us the probability that x2 is equal to 1. So these would be valid, and we're accounting for every possible combination, so that we should be fine. In combination, in terms that they give us these outcome over here. Hence, we can express these in terms of, we can just play with these equations. This is what I mean by in this part over here. We can just play with these equations so that we can express these values over here, these ones over here, and just substitute them. So they become this. If we just do some algebra, we can express this probability over here like this. We can express this probability over here like this, and then we can just substitute it, and we can just make these expression. So once we do this expression, we can notice that this simplifies. If we have two we subtract twice the probability that x1 is equal to 1 and x2 is equal to 1 over here. Over here we subtract it twice, and then we have here we add them twice again. So these and these should eliminate these over here, which would just leave us with the probability that x1 is equal to 1 plus the probability that x2 is equal to 1. And that it would leave us with these. And what is P plus Q? P plus Q is this as well. So that proves that E is equal to x1, that the expected value of x1 plus x2 is equal to the probability that x1 is equal to 1 plus the probability that x2 is equal to 1, which would be equal to P plus Q. And we have already established that P plus Q is equal to the right side of this equation. So this is how we prove linearity of expectations for two indicator random variables. Thank you.